All right, today we're going to talk about bonds that hold molecules together. They're called intramolecular bonds, and then we're also going to build molecules. And then later on, we're going to talk about the bonds that are inside molecules because it's very important to their chemistry and how things behave. So one of the things I always show people in class is these two molecules here. You look how similar they are. So here's one molecule over on the left. The other. That's called a benzene ring. This represents carbons here. They got hydrogens on the outside. Then you've got a 3-carbon chain attached to the benzene ring. And so the only difference in these molecules is out here at the end. This represents nitrogen here. So you get a little nitrogen group called an amine group. And then you have a nitrogen, but right there you have a carbon with 3 hydrogens, which if you had a carbon with 4 hydrogens would be methane, but that's called a methyl group. And so the thing is the structure, the shape of these molecules determines how they behave. And so this is actually Adderall. This is the molecule Adderall that some people take for ADHD, and this is crystal meth. And so now you might say, well, don't say that, Mr. Vaughn just said that crystal meth and Adderall are the same thing. It didn't say that. They have the same shape because actually they're both fitting into dopamine receptor sites. And so that's what chemists know, is the shape of molecules determines their behavior, and what they're made of determines their behavior. And we'll talk later in the notes about how the shapes of painkillers all have to be similar because they're fitting into opioid receptor sites. And the way you smell things, things that have similar smells to you, like things that are minty, we typically do a lab in class over that. Well, obviously this year we can't do that, but things that have minty smells, they have similar shapes of molecules, and things that have sweet smell, like your fruits and stuff like that, they have similar shaped molecules. So the shape of molecules matters, which is why we're going to be putting compounds together and building molecules. So today we're just going to talk about what kind of bonds hold things together. They're either ionic, metallic, or covalent bonds. And so again, bonds are just, you can either have a bond by one element giving electrons to another, or they can share them. And a lot of times what we'll end up doing is, to determine how many bonds are holding molecules together, we need to know how many valence electrons an element has. And hopefully you remember this, because a real core chemistry thing is the number of valence or outer shell electrons that an element has depends on where it is on the table. Things in column 1A have 1 valence electron. Column 2 has 2, 3 has 3, and then 7, 8. Remember, all the elements would love to have 8 in their outer shell, which is why they combine with each other. They don't really combine with anything because they already have 8. And so that's how we can determine valence electrons based on where they are on the table. So again, that's what this is pointing out here. They're all trying to follow the octet rule, which is, again, they all like to have a noble gas configuration, is really what the octet rule says. But remember, noble gases are in column 8. They have 8 valence electrons. And what they're really trying to do, which we talked about early in the year, was with electrons, is they're filling up s and p orbitals. The s orbitals, there's always one s orbital that can hold 2 electrons. There's always 3 p orbitals that can hold a total of 6. You put the s and p orbitals together and you get 8. And so that's what they're actually trying to fill up. This is, remember, the s section. This is the p section. You put those together, you get a total of 8 electrons. And so that's what they're all trying to do. That's why they gain or lose electrons or share electrons. First thing, so we're going to look at different types of bonds: ionic, covalent, metallic bonds. An ionic bond is typically, and this is just a generalization, so let's say this is a fabulous periodic table that I'm going to draw here. I mean, I'm not going to do actually the way it looks like, but remember there is a zigzag line over here somewhere that looks something like this. And one of the things I'm pointing out is on this side of the zigzag line you have metals, and over here you have nonmetals. And so typically your ionic bond is between a metal and a nonmetal. Not always true. That's, like I say, it's a generalization, but it's one way to look at it. So how do they go together? Metals, remember, they have 1, 2, or 3 electrons in their outer shell. They would love to give them to the nonmetals because they have like 5, 6, or 7. And so that's a great way for the metals to give electrons to nonmetals. And then, once a metal gives up an electron, it becomes a positively charged. A nonmetal accepts an electron, it becomes negatively charged, and opposites attract, and that's what holds these ionic compounds together. So I'm going to show you quickly how to do dot notations for ionic compounds. Again, we just kind of fly through these really quickly. We spend most of our time in this chapter talking about dot notations for molecular compounds or groups of nonmetals. But let me show you real quick how you would represent an ionic compound. So first of all, the dot notation for that, I'm going to rewrite it here, it's a little larger. First thing you do for dot notation is you find the number of valence electrons they have and use dots to indicate how many valence electrons they have. Now sodium's in column 1, so it has 1 valence electron. So you're going to write 1 dot. It doesn't matter where we put it, somewhere around the sodium there. So that dot represents its valence electron. Then you find the nonmetal. Chlorine's got 7. Okay, and so you're going to put 7 dots. What you do is you put 2 in each corner as though it's like in a box here until you get to 8, if that's how many it had, but it only has 7. So 1, 2, 3, 4, 5, 6, 7. Okay. Now, one of the things that I forgot to mention at first when you're just dealing with ionic compounds is that the first thing you need to do to know how many sodiums and how many chlorines you need to go together is actually to cross the charges like we did at the beginning of the year. So what we would do is we'd say, okay, Na, there's its symbol, and chlorine, we're going to write the formula for sodium chloride, and then again, you look at the charge of sodium, it's in column 1, it's +1. Chlorine is in column 7, so remember we love to take an electron, so it's -1. So they go together in a 1-to-1 ratio. You cross the charges, and we know that the compound is NaCl, which is why I just wrote 1 sodium and 1 chlorine. Now look at why the dot structure is showing us why they go together that way. The reason they go together in a 1-to-1 ratio is because sodium's got 1 electron to give to chlorine, so it gives that electron to chlorine. So that electron, again, is going to go over to chlorine. Now sodium will be +1 because it lost a negative. Remember, it lost an electron. And now chlorine is gaining that electron from sodium. So look how many chlorine now has, 8. Now after sodium loses that 1 electron, the next level has 8 in it. We don't need to draw those dots there. But now chlorine's -1. And so that's why they go together, because now opposites attract. It's an electrostatic charge that holds them together. And so that is our formula for an ionic compound between sodium and chlorine. I'm going to do one more and we'll move on. Again, the compound between aluminum and bromine, the first thing you need to know is, well, how many aluminums and how many bromines would go together? So we're going to write a formula for that. We're going to cross the charges to do that. So aluminum is here on the periodic table. And so remember, this in column 3. They would give away 3 electrons, so aluminum would be +3. And then bromine, again, is out here. And it is in column 7. It would love to have 1 electron. And so you cross the charges to put them together. And so our compound would be AlBr3. All we're doing in this ionic dot structure is showing why that actually happens. We're just trying to show you, from the beginning of the year, why it works that way. So this is telling us, okay, it's going to be 1 aluminum, and it's actually going to be combined with 3 bromines. And hopefully you will understand why as we draw this. Now remember, when you're doing a dot notation for it, you need to draw the number of valence electrons they have. Aluminum is in column 3. It's got 3 valence electrons, so I'm going to put 3 dots to represent its valence electrons. Bromine, again, is in column 7. So it's got 7 dots around each one of them, because that's how many it would start with. It would have 7 valence electrons. So each dot represents a valence electron. Each one's got 7 around it. And look at why they go together the way they do. Aluminum's got 3 to give away. The reason it doesn't go 1 aluminum with 1 bromine, because that bromine can only take 1, and now it has a -1 charge because it accepted 1 of the electrons, but aluminum still has 2 to give away. So what it has to do, it has to have another bromine has to come along, and then give that electron to that bromine, this electron to this one. Now it's +3 because it got rid of 3 electrons. Each of those 3 bromines accepted 1 electron. They're a total charge of -3. The total charge of that compound is 0 because all we're doing is keeping track of electron movement. So that's why that compound goes together as AlBr3. Aluminum's got 3 valence electrons to give up, but each bromine can only take 1. And again, so that's how to do dot notation for ionic compounds. We'll look real quickly at some of the properties of ionic compounds. The fact that they are held together by, now sodium is +1, chlorine's -1 once you put them together, because sodium gives an electron to chlorine. It indicates some of the properties they have. First of all, we can say that ionic compounds typically form between metals and nonmetals. They have high melting points, and the reason why is if we look at more than one salt, that's salt in this case, molecule or formula unit, they opposites attract. So adjacent molecules, if this has negatively charged, it has an extra electron, and sodium gave this electron to this chlorine, it's positively charged, opposites attract, so they have this strong bond between molecules. That's called an intermolecular bond that holds them together, and so they have high melting points. They're very difficult to break apart. So if you have salt and you're trying to heat it up, it'd be very difficult to do. They're typically soluble in water, and we'll talk more about this later because the reason is water is a bent molecule. They share electrons between hydrogen and oxygen, but they got some unpaired electrons that take up space over here, which crowds the hydrogen together on one side. They don't share equally. Oxygen's more attracted to electrons than hydrogen, and so hydrogen's positively charged and oxygen is negatively charged. And so water pulls apart ionic compounds into individual chlorines and sodiums. The hydrogens would be attracted to the chlorine, pull it apart, and over here, if we had a sodium, it would be attracted to the negatively charged oxygen. So they are soluble in water because water can pull apart ionic compounds. They are typically good conductors when you put them in water because when you put water pulls them apart into their individual ions, and you have a battery, electrode connected here, what you have a battery is having a chemical reaction that's producing electrons that are going in there, and another reaction that's accepting electrons here. And so when water pulls apart the sodium and the chlorine, since the negative electrons are coming into this electrode from the chemical reaction, sodium being positively charged would be attracted to them and would pick up electrons. So the sodium would move over here. The chlorines would give up electrons to the positively charged electrode, and then you have this flow or current or flow of electrons. And so they're typically good conductors, which means we call them electrolytes. Things that are good conductors in water are electrolytes. And then there's one more thing there. They're crystalline solids at room temperature because usually, they stick together very well. Now, bonding that holds metals together. Now, I'm talking about individual metals, like if you have a sheet of aluminum or a sheet of copper or a sheet of gold. What holds them together? That's a different type of bond, and let me explain why. It's called a metallic bond. And so let me draw a couple of aluminum atoms here. And all I'm going to represent are the valence electrons. I'm going to use dots to represent the valence electrons that each one has. And here's how metals stick together and this type of bond makes them unique. This is called a metallic bond that holds them together. It is, again, it says here it's the attraction of delocalized free-floating valence electrons around these metal ions. Remember, the charge of the core of any aluminum atom would be positive, but these valence electrons, remember, aluminum's got 3 electrons in its outer shell. It would love to get rid of those 3. So when you have a whole bunch of aluminums together, they're not holding on to those electrons very well because they would like to get rid of them. And so instead of them just being given to other aluminum atoms, what's happening is these electrons are just free roaming. So there's this sea of electrons that are surrounding these aluminum, these positive aluminum, the core of each aluminum ion would be positively charged. And so this sea of free roaming electrons, that's what's called a metallic bond. And so it gives metals their unique properties. It means metals are malleable or ductile. You can hammer them into shapes, and the reason why is because this aluminum is not really connected to the aluminum next to it. It's just generally attracted to all the electrons around it. So if you hit it with a hammer, you could basically, hammer it into a shape where they're all in a row because it's not going to break because there's no real bond between them. They're just generally attracted to all the electrons that are floating around them. And so since all these electrons are free to roam around, that's why metals are great conductors of electricity because that's what electricity is. It's free roaming electrons. So if you just put a battery electrode, let's say this is an aluminum rod, put in a battery electrode here with a negative charge and a positive charge over here, now all these electrons will start flowing there and it'll accept more electrons. And so that's why metals conduct electricity. That's why they're malleable, because it's malleable. That's because you have these free roaming electrons between metals, and that's in a metallic bond. And the last thing for today is talk about whether or not you would have an ionic or covalent bond holding something together. Remember I said typically an ionic bond is between a metal and a non-metal. That's a generalization. We use what's called the electronegativity values between elements to determine exactly what kind of bond they're going to have. So here's an example of some electronegativity values. If you've forgotten from the beginning of the year, electronegativity is the attraction for electrons. It increases across and decreases down. Now let's revisit that real quickly and explain why. The attraction for electrons. Think about metals, the whole column 1. Do they want to gain or receive electrons? They have one on an outer shell. They don't want electrons. They want to get rid of the one they have. So they have a low attraction for electrons. And as you go down the table, further down the table, there are more levels of electrons. And so they want to get rid of an electron. They really can't hold on to them because they've got so many levels of electrons. But as you go across the table, they have like 7 in their outer shell. Notice it stops with column 7 there, fluorine. They would love, notice this has the highest electronegativity because fluorine's got 7 and it would love to have one more, and it's really small, so that electron would be very close to the nucleus. When they get larger and larger, again, compared to the other side, they would love to have electrons, but these are larger and larger, they have more levels of electrons. So electronegativity, again, increases across and decreases down. So all you have to know exactly what type of bond you have is the difference in electronegativities. If the difference in electronegativities between two elements is greater than 1.7, it's an ionic bond. If the difference is between 1.7 and 0.31, we call that a polar covalent. They're sharing electrons but not equally. That's what polar means. It's like you've got a positive and a negative side. And if the difference is between 0.3 and 0, that's called a nonpolar covalent bond. Again, that's pointing that out here. And again, I put you a kind of visual for that. The difference between electronegativity values between two elements is between 0 and 0.3 nonpolar covalent. The difference is between 0.3 and 1.7 polar covalent and ionic bond. And again, let's compare our Na and Cl that we talked about earlier. Let's see if hopefully they're on here. Sodium is 0.9. Chlorine is 3. If you just subtract 3 minus 0.9, the difference is 2.1, and that's an ionic bond. And that's all you have to be able to do to know exactly what kind of bond would be holding two things together. All right, so let's, I'm just going to quickly fly through these because this is not a big part of what we do, and we're wrapping this up for a day. So it says indicate the more polar bond, and let me show you just real quickly how you can do that. So look at your electronegativity values. So carbon's 2.5, and oxygen is 3.5. The difference, 3.5 and 2.5, is 1, so that's a polar covalent bond between carbon and oxygen. And here's the way you show polarity in a molecule, is you draw an arrow going towards the element that has the highest electronegativity, because what we're saying is oxygen, if they're sharing electrons, oxygen's more attracted to them than carbon. So you draw an arrow showing that, and you put a little plus sign on this end of the arrow. So that means that when they're sharing electrons, they're hanging out closer to oxygen than carbon, which means that oxygen will be slightly negatively charged and carbon slightly positive because the electrons will be hanging out closer to oxygen. Carbon-nitrogen comparison, again, carbon's electronegativity value is 2.5 and nitrogen's 3, so the difference again is 0.5. So in this case it says indicate the more polar bond. This would be the more polar bond there because the difference there is only 0.5. But again, when you're looking at where the electrons are hanging out, you do a little arrow like that to show the electrons are hanging out closer to nitrogen than carbon because it has a higher electronegativity. And again, I'll show you one more and wrap it up. Like it says, which bonds are polar and which are nonpolar. You got a carbon-hydrogen bond, you got carbon-carbon bond, and you got a carbon-oxygen bond. Don't worry about the two lines there for now. We'll talk more about that later. So here's the thing. Carbon is 2.5, hydrogen 2.1, and carbon again is 2.5 and 2.5. So in this case, they share equally because when you subtract 2.5 and 2.5, you get 0, and that's a nonpolar covalent bond. In other words, what nonpolar means, one side's not positive or negatively charged. They're just sharing electrons equally. So, and then carbon there and oxygen, the differences are again 2.5 and 3.5. So the difference here is 0.4. When you go, what kind of bond would that be? That'd be a polar covalent bond. The difference here is 0, so that would be a nonpolar covalent bond, and the difference here is 1. And again, that would be a polar covalent bond. But if it's saying which bonds are polar, so the polar bonds in this case are carbon-hydrogen and carbon-oxygen. And which is the most polar bond? Again, it would be this one, because again, it's the one that has the greatest difference in electronegativities, would be the one that's the most polar. Again, to show where the electrons are hanging out, you would do that. We can't do that here. They're equally being shared. And in this case, the electrons are hanging out closer to the carbon because, again, it has a higher attraction for electrons. So that's it. Next time, I'm going to show you how to start building molecules. Good luck.